Hello, and welcome to this webinar hosted by ECHA on the assessment of the validity of QSAR results under dossier evaluation. Today, we will present the rich requirements for the use of QSARs as adaptations to standard information requirements and the most common issues ECHA finds when assessing the validity of QSAR studies. The objective is to let you understand what information ECHA requires to assess the validity of QSAR studies and how to improve the information you have already submitted in case of non-compliance. My name is Andrea Gissi. I work in the Computational Assessment Unit of ECHA, where I deal with QSAR cases for both human health and environmental endpoints. In addition, I am the project and product manager of the OECD QSAR Toolbox, and I represent ECHA in OECD activities related to QSARs. My colleagues Munir and Doris will also be presenters today. I let them introduce themselves.
Hi, I am Munir Bouift. I joined the agency about a year and a half ago. I am a member of the Alternative Methods team of the Computational Assessment Unit of ECHA. Part of my tasks are on the assessment of QSAR adaptations and predictions. New approach methodologies are another area of work here. I was working on the development and application of alternative methods, and especially their validation at the European Center of Validation of Alternative Methods. In this webinar, I will present the REACH requirement for the use of QSARs as adaptation to standard information requirements. And now I hand over to my colleague Doris.
Hello, my name is Doris Hiermann. I work at the European Chemicals Agency since 2007. My work areas are QSARs and assessment of QSAR predictions, as well as new approach methodologies related to environmental endpoints. Another work area is the assessment of persistency and bioaccumulation potential in relation to the identification of PBT and VPVB substances, which links quite nicely with the QSAR area, as the QSAR predictions are rather frequently used for the assessment of degradation and bioaccumulation endpoints. My part in today's presentation will be the most common issues with the compliance of QSAR results. And now I hand over back to Andrea.
If you are following the event on June 3rd from 11 to 1 p.m., you can ask us questions using Sli.do. To do so, visit the website Sli.com and insert the event code QSARs 2021. Alternatively, you can also contact ECHA at the address echa.europa.eu/contact. After the event, the video recording, presentations, and Q&A will be made available at echa.europa.eu/webinars. Now we are ready to start. The presentation today is divided in the following parts. First, an introduction to REACH and ECHA. Most of you should be very familiar with this topic, so we will only spend a few minutes here. Then, we will take a look at REACH requirements for the use of QSAR, which are at the basis of ECHA's assessment. After that, we will see the most common issues with the compliance of QSAR results, with anonymized examples from real cases. Then, we will see for which requirements and endpoints QSAR models are available in the section QSARs as adaptations in REACH, coverage of information requirements. We will then see the take-home messages in the conclusions. What we are not going to see today are slides that specifically address the OECD QSAR Toolbox, a software for chemical hazard assessment co-developed by ECHA and OECD. ECHA will organize a separate webinar about it. We are not covering it today because in REACH registration, the toolbox is mainly used for read-across studies, which are evaluated according to the read-across assessment framework, known as RAF. For QSAR predictions obtained with the toolbox, the QSAR assessment discussed today applies. To set the scene for our presentation today, let's see a brief introduction to REACH and ECHA and how QSARs fit in it. This part will only take a few minutes and will only cover the aspects relevant to today's presentation. REACH is the European regulation on registration, evaluation, authorization, and restriction of chemicals. One of the most important concepts set by REACH is that industry is responsible for the safe use of substances they produce or import. The safe use starts from knowing the intrinsic properties and hazards of substances. The minimum set of information that needs to be reported is called the standard information requirements and depend on the production volume of the chemical. The format to report this information is Euclid dossiers. Higher volume is associated with higher requirements. ECHA is the European Chemicals Agency. It has been established by REACH in 2007 and is nowadays responsible for the implementation of a number of chemical-related regulations. One core process under REACH is dossier evaluation, where ECHA checks that the information submitted by industry for their substances is compliant with information requirements. Only in case of non-compliance, ECHA communicates with REACH registrants. This is why it is difficult for ECHA to provide examples of accepted information. This presentation focuses on QSAR assessment within this process. Another core process is substance evaluation, where ECHA and European member states use the information in the dossiers to identify substances of very high concern for which risk management measures are needed, such as authorization or restriction. Here, we have a visual representation of the main processes and actors of REACH. First, the industry. Industry gathers information and is responsible for risk management. Some of this information may come from QSAR studies. Then, in the middle, we have ECHA and member states that control the information and eventually request for more. Here, under dossier evaluation, is where ECHA assesses the validity of QSAR studies provided by industry. Finally, the European Commission uses all the information to decide on the applicability of community-wide risk management measures, such as authorization, restriction, and harmonized classification and labeling. REACH states that testing on vertebrate animals should be used only as last resort. ECHA therefore promotes the correct use of alternative methods in many ways, such as contribution to related OECD activities, such as the OECD QSAR Toolbox, of which is co-owner and co-developer with OECD, or the contribution to the drafting of new OECD guidelines that include non-animal methods, such as the new guideline on defined approaches for skin sensitization. ECHA also participates in the international project on accelerating the pace of chemical risk assessment, APCRA, where new approach methodologies are used. ECHA also makes REACH data more and more available so that developers of new methods can use this data to train or challenge their models. Finally, ECHA has prepared a number of guidance and supporting documents related to alternative methods, such as the report on the use of alternatives to testing on animals for the REACH regulation, also known as Article 117.3 report. One possibility to prevent animal tests allowed by REACH is to adapt the standard information requirements. In this case, an appropriate justification is required. There are two types of adaptations under REACH: the endpoint-specific Annex 7 to Annex 10 Column 2 adaptations and the Annex 11 general adaptations that in principle can be used to cover any endpoints. One of the Annex 11 adaptations is testing not scientifically necessary, which includes QSARs among others. Rich Annex 11 also indicates the requirements for each of these types of adaptations. Munir will now present the Annex 11 requirements for the use of QSARs.
In the second part of the webinar, we will discuss the REACH requirement for the use of QSARs. We will have a look at the legal basis and the guidance document related to the use of QSARs, and we'll also talk about some of the elements crucial for the use of QSAR as adaptation to standard information requirements. REACH Annex 11 described the requirement for the use of QSARs as adaptations to standard information requirements. When ECHA assesses a registration dossier that contains an endpoint study record with a QSAR as adaptation, we'll verify that the study meets those requirements. The first requirement is that the model should be scientifically valid, and this criteria are included in an OECD guidance document that was released in 2007. The second requirement is that the substance should be within the applicability domain of the model, and here some criteria are included in the REACH guidance R6. The same applies for the third requirement about the adequacy of the results for the purpose, and criteria are included in the REACH guidance R6. And finally, adequate and reliable documentation of the applied method. In other words, both the model and the prediction should be provided, and there are reporting framework for that. At this point, I would like to highlight that the OECD guidance document and the REACH guidance R6 are our main sources for assessment of QSARs. The validity of the model can be assessed by checking the OECD principles of QSARs, and these are 5. A defined endpoint, an unambiguous algorithm, a defined domain of applicability, appropriate measures of goodness of fit, robustness, and predictivity, in other words, measures of performance, and a mechanistic interpretation if possible. As you can see, the last principle is not mandatory. It says if possible. That's why in our assessment, usually we will not use this point as motivation for rejection of a QSAR adaptation. As a reminder, the OECD principles only cover the first REACH condition for acceptable QSAR results. That is the scientific validity of the model. But let's see how these principles of the scientific validity of the model relates actually to QSAR modeling. This webinar is not about how we develop a QSAR model, but rather their use in a specific regulatory context. But this will help us, I hope, to understand a bit better these principles. On the left side, we have our principle for the scientific validity. And on the right side, a chart that describes a generic workflow for QSAR modeling. Very briefly, when developing a QSAR model, the starting point is the data that is collected and curated in terms of quality and content. Then this data is split in different sets. The training set will be used to build a method or algorithm to predict a certain property or endpoint. The test set and external set will allow to provide measures of the performance of the model. Then based on that, we'll define an applicability domain. And when possible and relevant, a mechanistic basis of the model is also provided. We can see that the part related to the data collection and curation is linked to the first principle on defined endpoints. A model cannot predict properties that are not part of its training set. There are many ways to build the algorithm, and this algorithm should be described in a transparent way. There should be as much information as possible to allow this algorithm or this method to be reproduced and assessed, which is the second principle. For the defined applicability domain in the QSAR model, I think it's self-explanatory, and this is the third of the OECD principles. The fourth principle about appropriate measures of goodness of fit, robustness, and predictivity are related to the measure of performance of the QSAR model defined by the test set and external set. Again, the mechanistic interpretation is not always possible and is not mandatory. It is important to highlight the difference between model validity and an acceptable prediction. The use of scientifically valid model is a prerequisite, and thus it is required, but not sufficient to obtain valid prediction. We could think of the model as the machinery or the tool, and the prediction as the result, and both the tool and the result or the outcome should be good. The principle of the scientific validity of the model for regulatory use have been agreed at OECD level, and we already mentioned the guidance documents or the QSAR principles. But the criteria for the assessment of the validity of QSAR predictions that are indicated in the ECHA guidance R6, there are no agreed principle at OECD level. But there are some OECD projects that just started that are tackling the revision of the QSAR OECD principle and also trying to establish a framework to assess the validity of QSAR model results. In principle, a model needs to be assessed only once for a specific purpose, while each individual prediction needs to be assessed individually, and this is the way we do it at the agency. This is an overview of the regulatory requirements of both the model and the prediction. All starts with the legal basis that is reached Annex 11 that defines the requirement for the use of QSAR as an adaptation to standard information requirement. These requirements are covered under OECD principles concerning the scientific validity, while the three others are covered in REACH guidance R6. We will discuss now those elements in details and will be using the chart you have in this slides as the reference in many slides that will follow, so that you can see where we are exactly in those requirements. So now let's see those OECD principles and have a look at the rationale and purpose behind them. For the defined endpoints, the intent of this principle is to ensure clarity and transparency in the endpoint that is being predicted by the model. And here endpoint refers to any physical property, a biological effect, would it be human health or ecological, environmental fate, that can be measured and then modeled and then predicted. Since a given endpoint could be determined by different experimental protocols and different conditions, it is really important to identify those experimental conditions that are being by the model, that are being modeled by this QSAR, and this defines our endpoints. For the algorithm, according to the second principle, a QSAR model should be expressed in the form of an ambiguous algorithm. And the intent of this principle is to ensure transparency in the description of the model algorithm. So information on how the model was developed, how descriptors, for example, are used to make the prediction for a certain property of interest, and what data was used in building this model. We know, for example, that in commercially developed model, this information is not always publicly made available. And without this information, the performance of the model cannot be established. The defined domain of applicability is needed because it expresses the fact that QSARs are reductionist by nature, which then have show limitation in terms of the type of chemicals that are being modeled, their physical properties, and also the mechanism of action for which the models can generate reliable predictions. According to Principle 4, a QSAR model should be associated with appropriate measures of goodness of fit, robustness, and predictivity. And this principle expresses the need to provide two types of information. One is the internal performance of the model, represented by the goodness of fit, and determined by using the training set that we discussed during when we saw the QSAR modeling workflow. And the second measure of performance is the predictivity of the model, determined by using the test set. So the fifth principle is about the mechanistic interpretation, and it says, if possible, it is not formally checked since it is an optional requirement. It's not always possible from a scientific viewpoint, but also it's not always possible to provide this mechanistic interpretation. So, but the absence of this mechanistic interpretation does not mean that the model itself is not potentially useful. But when this mechanistic interpretation is possible, it will add strength to the confidence in the model, added to the other principles that we discussed, the four first principles. The assessment of the model validity is a necessary but not sufficient step in assessing the applicability of QSAR results. Assuming that a model is considered valid, the next and crucial step is to evaluate the validity of prediction for a specific substance. And the question being asked here is the outcome of the model, this outcome, could it be applied for a specific substance, and is this outcome valid? So this is not a very trivial question, but it could be broken down into the following questions that we have in the three last bullet points. Is the substance within domain? Is the prediction adequate for the purpose? And is there enough documentation to substantiate this, these claims? And those conditions are further specified in ECHA guidance R6. We already discussed the first element on the scientific validity of the model, and now we will spend some time on the other elements. And we will start with the applicability domain. There are no agreed definition or methodology at regulatory or scientific level about of the applicability domain. Basically, each model developers applies its own method, but one definition could be the one that you see in the screen, which is the applicability domain of a QSAR model is the physical, chemical, structural, or biological space, knowledge or information on which the training set of the model has been developed, and for which it is applicable to make predictions for new compounds. So the applicability domain of a QSAR can be thought as a theoretical region in a multidimensional space in which the model is expected to make reliable predictions. This region depends on the nature of the chemicals in the training sets and the method used to develop the model. Ideally, the applicability domain should define the structural, physiochemical, and response space of the model. If a QSAR is based on physiochemical descriptor, the interpolation space, in other words, its coverage is defined by its descriptors. The interpolation space of one descriptor model is simply the range between the minimum and the maximum of the values of that descriptor. And the interpolation space of multi-dimensional multi-descriptor models are more complex. Here we can see on the right side a simple representation of coverage with two descriptors, with the black dots in this graph representing the substances or chemicals in the training set, and the yellow dots would represent the substances that we would like to predict using these models. So for the yellow dot that is in the bottom right, we can see that is outside domain, and the prediction could be considered as non-reliable, whereas for the other one, which is inside domain, within domain, and we could consider that the prediction would be more reliable. How do we assess if a substance is within the applicability domain of a model? We usually use the model developer definition, which is our starting point, and we also consider other aspects as relevant. And these include the elements that we already mentioned: the descriptor domain, the structural domain, the mechanistic domain, and the metabolic domain. And basically, the determination of whether a chemical falls within the applicability domain of model is based on an assessment of the similarity between the chemical and the training set using those elements. These elements could be seen as different layers of the applicability domain. So in the first layer, which is the descriptor domain, identify if chemicals falls in the range of physical properties of that model. This is usually done on the descriptor values, such as the molecular weights, log P, solubility, used that are present in the structure in the training set. The second layer defines the structural similarity between the substance that we would like to predict certain property, and this is defined by correctly having those predictions in the model. The structural domain is usually based on the fragment present in the structure in the training sets also. The third layer includes a mechanistic verification by assessing if the chemical contain specific functional groups assumed to cause the effects of interest. The mechanistic domain takes into account the different mechanisms of effect or toxicity covered by the structure in the training set. You can see here that it's always the properties of the substances in the training set that are taken into consideration for the applicability domain. The same applies for the fourth and final layer, which is the metabolic check based on an assessment of the probability that the chemical undergoes metabolic activation. And this is applicable only if metabolism is relevant for the endpoint. Again, there are many methods and ways for defining the applicability domain. A simple way is to use the range of the chemical descriptors for the chemical in the training set. In this example of the software tool EPI Suite that is very popular and developed by the US EPA, it uses two descriptors, the molecular weights and log P, and the developer provides the ranges of both descriptors to define the applicability domain, as we can see in the right side of this in this slide. So we can see the minimum and maximum values of the molecular weights, and also minimum and maximum values for log P. And the software developer also suggests to combine this approach of parametric domain with the fragment-based domain, or the fragment-based approach. in the structural domain, we use the list of fragments and eventually their number of occurrences per molecule in the training set to define the structural domain. One possible approach is to take the molecule that we would like to use in this model and to split it in molecular fragment to check whether all the fragments are represented in the training set of the model. Only molecules with the fragment represented in the training set are considered within domain. So here again, it is a screenshot from EPA suite by the US EPA, and the developer suggests to use this method together with the first one that we saw, which is the descriptor domain. In addition to the descriptor and structural domains, another useful element in the applicability domain definition is the understanding of the mechanism of action of the substances used to develop a model. So a model can predict substances that act according to the same mode of action covered by the substances in the training set. As an example, there are many bioconcentration models that calculate the PCR potential based only on the log P of the substance, assuming accumulation in the lipid tissues of fish, and other mechanisms are not always considered. If we have evidence, for example, or suspect that the target substance might bioaccumulate with a different mechanism, then we would consider that this substance is out of the mechanistic domain. The metabolic domain is defined as the extent to which metabolism is taken into account by the model. As you know, metabolism can increase or reduce the toxicity of the substance, and many models are able to take into account this by, for example, simulating the expected metabolites and predicting also their effects or their toxicity. These simulators will have their own applicability domain, and substances outside the domain of metabolic simulator should be considered also outside the metabolic domain of the model. As an example, many skin sensitizer cause their effects after biotransformation. To take this into account, some QSAR models simulate skin metabolism and then predict the skin sensitization potential of the metabolites too. If there is enough evidence that the target substance might undergo metabolic transformation not accounted by the model, then the substance should also be considered out of metabolic domain. Now let's go back to the reach and the requirement for QSARs. We discussed the scientific validity, we spent some time on the applicability domain, and now we will see the last 2 points about the adequacy and documentation. So the third requirement is that the result should be adequate for the intended purpose, and in this context, the purpose relevant for ECHA is mainly adaptations of rich information requirements. So this question about adequacy of the results arises because most available models were not really tailor-made for the regulatory needs, and automatically these models will have biases that we should account for in the context of their prediction. So a model can be biased towards certain type of chemicals or certain type of predictions, for example, negative rather than positives, and such biases should not affect the validity of the model, but they could affect their applicability for specific purpose. So for the adequacy of the results, usually We verify the input structures, because choosing the correct input structure is not always trivial, especially for UVCBs or multi-constituent substances. And the reliability of the prediction could be assessed by considering the following aspects, in addition to the aspect that we already discussed about the applicability domain and so on. So we assess the reliability of the input parameters. For example, if we are using molecular weight and log P as an input parameter, so we would check that, for example, log P is a reliable. The values provided for log P are reliable. We will also assess the presence of analogs in the training set and the accuracy of their prediction by that model. And we will also assess the consistency of the prediction with other information if available for that substance. For example, as an example, if we have short-term toxicity to fish and we are predicting long-term toxicity to fish, then we would check that there is consistency between those information. And according to Annex 11 of the REACH regulation and the last point of those requirements, we need to have adequate and reliable documentation for the applied method. And the applied method means both the model itself and the prediction. There are different reporting formats that have been developed to capture this different type of information. So the description of the model itself is contained in the QMRF, which stands for the QSAR model reporting framework. And this describes or contains information about the algorithm, how it was developed and how it was validated based on the OECD principle. And the QMRF must include information on the predicted endpoint, including information on the experimental protocol and the data quality used to develop the model, the definition of the algorithm, the descriptors that were used in the model, and the applicability domain. And also measures of performance, which means estimates of goodness of fit, and the predictivity of the model using the test set and validation set. The second type of information is about the prediction itself. And this is contained in the QPRF, which stands for the QSAR Prediction Reporting Framework, that will provide information on how the prediction has been derived for a specific with a specific model. And the information must include, the QPRF must include information on the model predictions, including the endpoints, a precise identification of the substance modeled, the relationship between the model substance and the defined applicability domain, and identities of close analogs, including consideration how they are predicted, and experimental data for analogs to support that prediction. Now I will hand over to my colleague Doris, who will walk you through the most common issues with the compliance of QSAR results.
Hi again. So I would like to explain you now what are the most common issues we have encountered with the compliance of QSAR results in the dossiers that have been submitted to ECHA. And I'm going to present also a number of examples to illustrate the issues. So here is an overview of the most common shortcomings. I will go through in more details in the next slides. The shortcomings are matched with the requirements in Annex 11 of REACH on the use of QSARs as an adaptation for standard information requirements. I'm going to address two aspects under scientific validity of the model, which is the definition of the endpoint and the measures of performance. Regarding the applicability domain, I will give you examples of issues we have encountered which are linked to the applicability domain as defined by the model developers, and also additional aspects to consider when checking the applicability domain, which are described in the REACH guidance R6. This is the REACH guidance related to QSARs and grouping of chemicals. Regarding adequacy, a frequent shortcoming we have seen is a mismatch between the structure that was used for the prediction and the substance identity information provided in the registration dossier. I'm going to address further issues related to the reliability of the prediction. And the last part addresses the documentation. And this is really very important for us, the authorities, to be able to assess the scientific validity of a model and the adequacy of a prediction. Here we distinguish between the documentation of the model and the documentation of the prediction. Before I start with the first topic, I would like to draw your attention to the graph in the upper right corner. There you can see the overview of the list of the most common shortcomings for you for a better orienteering at which topic we are. So we start now with the definition of the endpoint, which is related to the scientific validity of the model. It is important to remember that models predict the endpoint and effects according to the experimental data they are trained on. So the trash in, trash out principle applies here. If the model is built on inhomogeneous data and effects, it is considered not well defined from a regulatory point of view for the purpose of meeting the information requirements. Here below, you see one example about the model for long-term toxicity to fish, mixing the studies of different durations and including also 40-day studies. So to explain the 40-day studies, we do not consider as long-term studies. The effects predicted in a model should match the effects measured by the defined test protocol. If the effects are different or do not include all the effects retrieved from a guideline study, then the predictions from the model are not acceptable to meet the information requirements. We have here presented examples on the Ames model. So the Ames model, if it's lacking the 5th strain, and a model for repeated dose toxicity predicting only the NOAEL. Measures of performance of the model are needed to estimate the reliability of a prediction. Without such information, it's difficult to judge the reliability of a prediction, and with that also the uncertainty. Profilers from the toolbox should not be used directly as predictions for the purpose of fulfilling standard information requirements. They are grouping tools for the identification of analogs, and measures of their performance to predict apical endpoints are usually not available. So this is the example to this topic. Now we come to measures of performance. Another common issue we have seen is that the training set is too small and therefore not considered robust. The minimum requirement is described by the so-called top-least ratio, which should be bigger or equal to 5. That means the number of substances in the training set divided by the number of descriptors. For a model with one descriptor, let's say a simple model based on log KW, it would mean that at least 5 substances have to be in the training set. Here we have an example related to ECHA, and ECHA includes more than 100 models for different chemical classes, but some of the models have really a limited number of training set chemicals, and in some cases the training set chemicals identity is not revealed when they are labeled as CBI or confidential business information. ECHA models are based on one descriptor, the log KW. Therefore, we consider ECHA class-specific models with training sets with less than 5 substances as not robust. Here we show you an extreme example of such a model. The algae EC50 model for the class substituted urea from ECHA version 1.11 was used in a dossier to build and is built only on one data point, which is even labeled as CBI, and together with the log KW limit. So we consider this as not scientifically valid model. Then we come to the topic of applicability domain as defined by the model developers. The AD we use here in this presentation quite frequently, and it stands for applicability domain. Some models, often the more recent ones, they support already the user with an automated check if the model is applicable for a substance. The definition of the applicability domain should be included in the documentation of the model. With this information, a manual check can normally be done. When the substance falls outside the applicability domain as defined by the model developers, the prediction is not accepted unless a good justification is provided. Occasionally, we do get predictions where the documentation produced by the software already states that the substance is not within the applicability domain. So this we cannot then accept as a reliable prediction. Here you can see an example of domain and reliability assessment automatically provided by a software. And in this case, it's the Vega software. And this makes automated assessments of applicability domain and reliability of their predictions. However, results still need to be critically investigated. The software results should not be automatically accepted. We recommend checking especially how similar the substances in the training sets are. In some cases, a software identifies similar substances, but when you look at the structure of the analogs, they are not that similar to the target substance, and hence there can be reliability issues with the prediction. In some cases, it could also be the other way around, that the software identifies shortcomings regarding the similarity of analogs, but the prediction could still turn out to be useful. We normally look first at the model domain as defined by the model developer, but additionally, we also look at the applicability domain layers as described in the REACH guidance R6. This is because when model developers define the applicability domain of their model, they may not always consider all aspects needed for a regulatory acceptable prediction. The applicability domain layers described in ECHA's guidance R6 include the descriptor, structural, mechanistic, and metabolic domains, which were introduced already earlier in this presentation by Munir. For this reason, a model may indicate a structure to be within its domain, but ECHA may overrule the automatic assessment of the model. So to illustrate you the issue, we present here an example with the log-KOC model in Episode. The model was used for a UVCB substance with some constituents having a log-KOW above 8. You can see the log-KOW of the training set chemicals highlighted here on the right side in yellow. The upper limit of the log-KOW range covered by the training set of the model is around 7. The model developers define the applicability domain as the range of molecular weight. The constituents were within this molecular weight range. We did check out additionally the descriptor domain and concluded that the substance is out of the log-KOW range for the KOC model, the one that is based on the log-KOW as input parameter. Now we come to the input structures. So this is a topic related to the adequacy of a prediction. For substances which contain more than one constituent or impurities or additives, the whole composition of the substance needs to be taken into account by predicting individually each constituent, impurity, and additive, or by selecting one or more representative structures and justify why the selected structure or structures represent the substance. Here we have 2 examples given. The first one is about a substance that has 3 constituents, which are quite different from each other. And a single representative structure cannot be selected, so the registrant should predict all 3 constituents individually. The other example is a UVCB substance with a variable alkyl branching, and the registrant should use 1 or more structures supposed to cover the worst case and justify the selection. Let's move to the next topic, which is the substance identity is not consistent. So here we have an example, again, of UVCB. So there is 2 structures that were used and described as the main components. However, a link between the structures and the composition of the substance was not given. So on the right side here in this box, you see the overview of the composition, where you see the 2 constituents with the higher percentage. However, these constituents 3 to 8, they need also to be addressed by prediction. What we also often see is that impurities are not addressed. This is especially relevant for properties such as biodegradation and bioaccumulation, when the substance could be potentially a so-called PBT or VP substance, VP-VB substance. Impurities down to 0.1% can be relevant for the assessment of persistency and bioaccumulation potential. Now we move on to the topic of reliability of the prediction. So this is the second topic under adequacy. We identified here 3 important aspects, which are the accuracy of predictions for similar substances, the reliability of input parameters, and the consistency with information from other endpoints. So I will give you some examples now on each of them. This is about the accuracy of predictions for similar substances. A model is expected to predict well similar substances if similar substances with experimental data for the target endpoint are available, and the model predicts these substances well. This supports the reliability of the prediction of the target substance. If you submit a prediction to ECHA, please think of identifying similar substances with experimental data if you can. This increases the confidence in the prediction. The definition of similarity is not straightforward. There is no really defined threshold. It depends on the endpoint and has some flexibility. But the complete lack of similar substances with data in the training set or otherwise may raise concerns of the applicability of the model to the target substance. Now, the second aspect under reliability of a prediction is the reliability of input parameters. Most of the models produce a prediction based on the input structure and its properties. The model can generate reliable predictions only if the input parameters are also reliable. Some models calculate properties of the substance itself. For some models, the user can manually insert property values. Such an example is the BCF-BUF model in EPISUITE. The user can enter manually a log KW value. We recommend the use of reliable experimental data for the log KW as input parameter if available. If the experimental values and the predicted value of a log KW differ significantly, this can lead to very different BCF predictions. And I'm going to show you now an example of such a case in the next slide. So here we have a prediction of a BCF of around 1000, which would indicate not B, so not bioaccumulating, using a manual input value for the log KW of about 9. The substance was within the applicability domain of the model, and the prediction was well documented. Now, the experimental value of the log KW we saw was 8 plus minus 1. So of course the numbers are not real, but the example was a real one. So it was 8 plus minus 1 and was provided in the dossier. the registrant decided to use log KOW of 9 as input to the model, which was the upper limit of the confidence range. Now, when you think about the relationship between the log KOW and the BCF, it's bell-shaped with a peak, let's say, around 6.5 or 7. Now, when you use the 9 for the log KOW, it leads to a predicted BCF, which is relatively low, while the prediction with the measured log KOW indicates a quite high BCF value. And the highest value with the lowest log KOW in the range given. So taking into account the uncertainty of the measured log KOW, the predicted BCF of the main constituent is either very low or above the threshold for bioaccumulation of the BCF of 2000. Therefore, the prediction is not adequate for the purpose of risk assessment and the PBT, VP, VB assessment. The last aspect of the reliability is consistency of the information for other endpoints. The information from the prediction must be consistent with the reliable information available for other related endpoints, which is usually not taken into account by the QSAR models itself. If it's not the case, then a prediction can be considered unreliable. Here we have prepared an example about aquatic toxicity. Let's say a reliable experimental short-term fish LC50 is available, and a QSAR prediction for fish long-term toxicity reports a NOAC, which is higher than the short-term LC50. And to illustrate better the example, I have here some numbers in the next slide. So let's say you have a chronic value predicted, a chronic value of 80 milligrams per liter. And as you can see, the predicted chronic value is much higher than the acute value for fish toxicity, which is given with 0.01 milligram per liter. What you would normally expect is a chronic value about 10 times or so lower as a rule of thumb. So the toxicity data for the other trophic level indicate rather low values for toxicity as well. So overall, this is an inconsistent data set and indicating an issue with the reliability of the prediction for the long-term toxicity to fish. The last part on the most common issues relate to the documentation. Please note that there is a difference between documenting the model and documenting the prediction. There is a format for the model called QSAR Model Reporting Format, or QMRF, which can be found in the REACH Guidance R6. Regarding the QSAR model documentation, we expect the following: the predicted endpoint, including information on the experimental protocol and data quality for the data used to develop the model, the unambiguous definition of the algorithm of the model, including descriptors and applicability domain, and an estimate of performance, such as goodness of fit, and the predictivity of the model, including information on training set and validation statistics. Ideally, it should be provided in form of a QMRF, but could also be included in the registration dossier directly in the endpoint study record, or reference can be made to a publicly available information on the internet. If this kind of information is missing, we cannot establish the scientific validity of the model. Regarding the prediction, so there is the format for documenting the prediction, which is called QPRF, and it's called QSAR Prediction Reporting Format, and can also be found in the REACH Guidance R6. Regarding the documentation of a prediction, we can expect that it includes the model prediction, including the endpoint, a precise identification of the substance that is modeled, the relationship between the substance and the applicability domain, and the identity of close analogs, including considerations on how predicted and experimental data for analogs support the prediction. Ideally, it should be provided as attachment in a QPRF, but could also be included in the endpoint study record. If this information is missing, the reliability of the prediction cannot be established. With this, I give back to my colleague Andrea, who will say a few words about the QSAR predictions for different endpoints, and then end this presentation with some take-home messages. So thanks a lot for your interest.
Thank you, Doris. In this last part of the presentation, we will now see how QSARs can be used to cover different information requirements. The following slides include observations on the current status. Not all rich requirements can be successfully adapted by standalone QSARs due to the limitations of the currently available QSAR models. One of the limiting factors is the complexity of high-tier endpoints. In general, QSARs works best when a high number of good quality experimental data is available. The mechanism of action or toxicity is well understood. The results of adapted experimental studies consider a limited number of effects that can be reasonably predicted by QSAR models. The use of QSARs as adaptation is possible for many physicochemical, ecotoxicological, and fate requirements. This is because experimental data of sufficient number and quality are available for building robust models. Mode of actions are well understood. The measured effects have good correlation with molecular descriptors, such as lipophilicity and aquatic toxicity in absence of specific mode of actions. The results reported from experimental studies include one or few effects, for example, mortalities as LC50 for fish short-term toxicity, that match those predicted by the QSAR models. The use of QSARs for high-tier human health endpoints should be limited to supporting information due to the complexity of the endpoints and effects measured by the experimental studies. For example, a QSAR model may predict an OL for repeated dose toxicity without providing information on target organs or other parameters that may be relevant to trigger further studies, such as specific organ toxicity or endocrine-related effects, or classification. Details on the underlying data used to build the QSAR model are often neither homogeneous nor of sufficient quality, and this is due to the limited number of available data, so model developers need to lower the quality standards for the data they use. Otherwise, these details may also not be reported at all, and this is a problem. The use of QSARs as adaptation is possible for some low-tier human health endpoints for the same reasons mentioned for environmental endpoints. A crucial requirement is that the predicted endpoint and results match those provided by the standard experimental test. As an example, for bacterial reverse mutation AIMS test, the QSAR model must explicitly consider all the 5 strains and metabolic activation as required by the OECD test guideline 471, or for skin sensitization, where the model must provide results that allow skin sensitization classification based on GHS and CLP criteria. Here we see a figure from the report on the use of alternatives to testing on animals for the REACH regulation, also known as Article 117 report. This figure illustrates the frequency of use of QSARs for different REACH endpoints. QSARs are in light blue and, on average, represent about 2.5% of the submitted information, at least for the endpoints considered in the report. In comparison, read across, the most used adaptation, has been used roughly 10 times more. We can also see that the endpoints where we know that QSARs have more chances to be successful are also the endpoints where QSARs have been used more frequently. These are bioaccumulation, aquatic toxicity, and low-tier human health endpoints. While for the complex endpoints, such as developmental and reproductive toxicity, we can barely see the QSAR bar in the plot. It is now time to conclude with some take-home messages. Sufficient information must be provided to allow ECHA to assess each of the criteria in REACH Annex 11 1.3. Document both the model and the prediction. The validity of each individual prediction must be justified. The use of a valid model is not sufficient. The availability of valid QSAR models depends on the requirement addressed. And here we conclude. We hope this webinar was helpful to understand the information to include in your registration dossier when using QSARs, and we thank you for your attention.